September 14th, 2023, Rockford, Illinois. The catastrophic failure that would cost Precision Manufacturing $340,000 in a single afternoon began with a sound that Senior Foreman Michael Torres had heard too many times in the past 3 years. The high-pitched whine of failing bearings in their new CNC stamping press, followed by the grinding screech of aluminum components tearing themselves apart under production loads they were never actually designed to handle. Torres hit the emergency stop as metal fragments scattered across the factory floor. The press, installed just 19 months earlier at a cost of $280,000, sat silent and broken. Its third catastrophic failure since installation. The manufacturer's service contract had already expired, and the repair estimate would exceed $60,000. Worse, the production line was dead until replacement parts arrived from overseas, a process that typically required 8 to 12 weeks. Standing in the wreckage of modern manufacturing efficiency, Torres remembered something his predecessor had mentioned during the retirement handoff 2 years earlier. Somewhere in the back of the facility, past the climate-controlled CNC machining centers and the automated assembly lines, there was equipment from the 1940s that the company had never bothered to remove. Equipment that supposedly still worked, though no one had powered it up in decades. Torres found the machines in Building 7, a section of the original factory that predated the modern expansions. Dust-covered but unmistakable, a massive stamping press sat beneath decades of accumulated grime. The nameplate was still legible, Warner & Swasey Model 4240, manufactured March 1943, Cleveland, Ohio. The press weighed 47,000 pounds according to the specifications plate, more than 3 times the weight of the failed modern equipment. What happened next would force Torres to reconsider everything he thought he knew about industrial machinery. After cleaning decades of dust from the lubrication points and electrical connections, he activated the motor control. The press came to life immediately, its cast iron frame absorbing vibration that would have shaken lighter equipment apart. The ram cycled smoothly through its full stroke. The mechanical clutch engaged precisely, and the press settled into a steady rhythm that Torres recognized immediately as superior to the modern equipment that had just failed. The 80-year-old machine required exactly 17 minutes of maintenance to return to full operational capability. It produced its first production part at 2:34 that afternoon with tolerances that matched the specifications of parts the failed modern press had been making. Over the next 3 days, while Torres waited for repair estimates on the broken equipment, the 1943 Warner & Swasey press ran continuously without a single malfunction, producing 12,147 stamped components with 0 quality rejects. The discovery raised questions that Torres couldn't answer. How could equipment, built during World War II, to outperform modern machinery designed with computer analysis and advanced materials? Why had manufacturers in the 1940s built machines 3 times heavier than contemporary engineers considered necessary? And most importantly, what had changed in industrial manufacturing that transformed reliability from a fundamental design principle into an unexpected discovery in a forgotten corner of an old factory building? The answers would require understanding not just the machines themselves, but the crisis that created them, and the engineer who refused to compromise on durability even when the entire manufacturing industry insisted his approach was wasteful and obsolete. October 22, 1939, Cleveland, Ohio. The argument that would define American industrial manufacturing for the next 50 years began in a conference room at Warner & Swasey's engineering headquarters, where 34-year-old chief engineer Robert Hartman faced a board of directors who wanted him to design machines that would fail faster. "Your specifications are economically irrational," board chairman William Patterson declared, tapping Hartman's preliminary drawings for the company's new line of stamping presses. "You're proposing cast iron frames that weigh 45,000 pounds when our competitors are building equivalent machines at 18,000 pounds. You want gear trains engineered for 50 million cycles when the average factory replaces equipment every 12 years. Your design costs $8,400 per unit to manufacture when we could build adequate machines for $3,200. Hartman had anticipated this resistance. He'd spent the previous 6 months analyzing failure reports from Warner & Swasey's existing equipment and visiting factory customers across the industrial Midwest. What he discovered was a pattern of preventable failures that stemmed from a single cause. Manufacturers were designing machines to meet minimum specifications rather than maximum durability. Mr. Patterson, I've documented 247 catastrophic failures in our current product line over the past 3 years, Hartman replied, sliding a thick folder across the conference table. Bearing seizures, frame cracks, gear failures, all caused by inadequate material mass and insufficient safety margins. The average repair cost per failure is $8, and the average downtime is 11 days. Our customers are spending more on repairs and lost production than they would have spent buying more durable equipment in the first place. Patterson remained unconvinced. Warner and Swasey competed in a market dominated by cost-conscious factory managers who evaluated equipment based on initial purchase price rather than lifetime operating costs. Manufacturers who built heavier, more expensive machines lost orders to competitors offering cheaper alternatives, regardless of long-term reliability differences. The market has spoken, Mr. Hartman. Factory managers want affordable equipment, not indestructible equipment. Your approach might produce superior machines, but it will bankrupt this company when customers choose our competitors' products instead. The tension in the room reflected a fundamental conflict in American manufacturing philosophy. Since the 1920s, industrial efficiency experts had promoted the concept of planned obsolescence, arguing that equipment should be designed to last exactly as long as its expected service life and no longer. Building machines to survive for decades was considered wasteful over-engineering that added unnecessary cost without providing measurable value. This philosophy was supported by influential voices throughout the manufacturing industry. Professor Edwin Morrison at MIT's Engineering School taught that optimal machine design required calculating expected service life and designing components to fail just beyond that point. His textbooks, which trained a generation of American engineers, included formulas for determining the minimum material mass required to meet specified performance targets. Hartman had studied Morrison's methods during his own engineering education, but his factory floor experience had taught him that theoretical calculations ignored crucial real-world factors. Machines operated in environments where dust, temperature variations, operator error, and inadequate maintenance created stresses that design calculations never anticipated. Equipment built to minimum specifications failed in these conditions, while machines with generous safety margins continued operating reliably. I understand the cost concerns, Hartman acknowledged, but I'm proposing we target a different market segment. Factories running continuous operations, facilities where downtime costs exceed equipment costs, manufacturers who value reliability over initial purchase price. Let our competitors serve the budget-conscious customers. We'll build machines for customers who can't afford failures. The board remained skeptical, but Hartman had one advantage that would prove decisive in the coming months. War was spreading across Europe, and American manufacturers were beginning to recognize that industrial capacity might soon become a matter of national security rather than just commercial competition. The machines needed for wartime production would require reliability standards that peacetime manufacturing had abandoned in pursuit of lower costs. The equipment that Hartman was proposing to build, heavy cast-iron frames, oversized components, generous lubrication systems, would become essential when American factories needed to operate around the clock producing materials for a war effort that would demand reliability above all else. December 18, 1941. 11 days after Pearl Harbor, the specifications that arrived at Warner and Swasey's Cleveland headquarters transformed Robert Hartman's controversial design philosophy from obstinate over-engineering into urgent national necessity. The War Production Board's requirements were explicit and uncompromising. Manufacturing equipment capable of continuous 24-hour operation, machines that could maintain precision through millions of cycles without recalibration, and systems designed to function even when maintenance was deferred due to skilled labor shortages. Hartman spread the government specifications across his drafting table and realized that everything his board of directors had criticized was now exactly what the military demanded. The war effort would require stamping presses producing millions of shell casings, lathes manufacturing precision components for aircraft engines, and milling machines creating parts for tanks and naval vessels. Equipment failure would mean production delays that could cost lives on distant battlefields. The first decision Hartmann made was material selection, and it would define the durability of American factory equipment for generations. While competitors experimented with lighter cast aluminum and welded steel construction, Hartmann specified grade 40 gray cast iron for all major structural components. The material choice increased frame weight by 170% compared to contemporary designs, but it provided vibration damping properties that no lighter material could match. Cast iron's molecular structure absorbed vibration energy through its graphite flake matrix, converting mechanical stress into harmless heat dissipation. This meant that a 45,000-pound cast iron press frame remained rigid and stable under loads that would cause lighter steel frames to flex and vibrate. The weight that critics had dismissed as wasteful over-engineering was actually performing essential damping functions that would preserve bearing alignment and prevent premature wear. Hartmann's bearing specifications were equally excessive by peacetime standards. Where conventional practice used single-row ball bearings sized for calculated loads, Hartmann specified double-row tapered roller bearings with 340% greater load capacity than static calculations required. He designed bearing housings with massive cast iron structures that maintained alignment even when thermal expansion or frame distortion created misalignment forces. The lubrication systems Hartmann engineered were designed for neglect rather than maintenance. Large oil reservoirs held 40 gallons of lubricant, enough to maintain proper bearing lubrication for 2,000 operating hours even if operators forgot routine service intervals. Gravity-feed oilers delivered constant lubrication to critical wear points without requiring pump mechanisms that could fail. The system was primitive by engineering standards but nearly indestructible in operation. Gear train design followed the bow. Same principle of massive overconstruction. Hartmann calculated expected torque loads, then designed gears with teeth 280% larger than minimum specifications required. The gears were cut from solid nickel-chrome steel billets rather than stamped or cast, a manufacturing process that cost 3 times more but produced components with grain structures that resisted fatigue cracking indefinitely. The clutch mechanisms that controlled ram cycling received similar attention. Instead of friction clutches that required frequent adjustment and wore out after 500,000 cycles, Hartmann designed positive engagement dog clutches with hardened steel teeth that could survive 50 million engagement cycles without measurable wear. The clutches were larger, heavier, and more expensive than conventional designs, but they eliminated the most common cause of stamping press failures. By March 1942, Hartmann's first production run of heavy-duty stamping presses was ready for delivery to factories producing ammunition components. Each machine weighed 47,000 pounds, cost $8,900 to manufacture, and incorporated design margins that peacetime engineers would have considered absurdly excessive. The presses were shipped to facilities across the industrial Midwest, where they would face the ultimate reliability test: continuous wartime production schedules that would run 24 hours daily for years without extended maintenance shutdowns. The validation of Hartmann's design philosophy would not come from engineering analysis or theoretical calculations. It would come from factory floors where machines either survived the demands of wartime production or failed catastrophically, taking critical manufacturing capacity offline when the nation could least afford equipment downtime. July 28, 1943. The Chrysler Tank Arsenal in Warren, Michigan, operated on a production schedule that would have been considered impossible before the war. The facility ran 3 8-hour shifts daily, 7 days per week, producing components for M4 Sherman tanks at a rate that required stamping presses to cycle continuously for months without extended maintenance shutdowns. This was where Robert Hartmann's heavy-duty equipment would either validate his design philosophy or reveal the flaws in his approach. Production Superintendent James Mallory had initially been skeptical of the Warner and Swasey presses when they arrived in December 1942. The machines were massive, requiring reinforced floor foundations and occupying 40% more floor space than the lighter equipment they replaced. Installation costs exceeded budget estimates by $12,000 because the existing concrete floors needed extensive strengthening to support the 47,000-pound press frames. This equipment is built like battleship armor, Mallory had complained during installation. "We're stamping transmission housings, not artillery shells. This is overkill." But 8 months of continuous operation had transformed Mallory's opinion completely. The Warner and Swasey presses had produced 847,000 transmission housings without a single catastrophic failure. Lighter presses from competing manufacturers installed in adjacent production lines had experienced 23 bearing failures, 14 clutch replacements, and 7 frame cracks during the same period. Each failure meant production delays averaging 6.8 days while repair parts were located and installed. The difference became most apparent during the night shifts when experienced maintenance personnel were unavailable and operators had minimal technical training. The Warner and Swasey presses continued running reliably despite operators who forgot lubrication schedules, overloaded the machines beyond rated capacity, and operated equipment with maintenance practices that would have destroyed lighter machinery within weeks. Hartman visited the Chrysler facility in August 1943 to document equipment performance. What he discovered exceeded even his expectations for durability. Bearing wear measurements showed less than 0.003 inches of clearance increase after 5.2 million press cycles, wear rates so low that the bearings would maintain acceptable tolerances for decades of operation. The cast iron frames showed no detectable cracks or stress concentrations despite continuous operation under loads that would have fractured lighter steel frames. Most remarkably, the massive gear trains showed virtually no wear. Hartman's decision to oversize gear teeth by 280% meant that contact stresses remained well below the material's fatigue limits. The gears could theoretically survive 500 million cycles, a service life measured in decades rather than years. The heavy construction that critics had dismissed as wasteful over-engineering was performing exactly as Hartman had predicted, providing durability margins that absorbed operator abuse and maintenance neglect. The War Production Board recognized the significance of this performance data. In October 1943, they awarded Warner and Swasey a contract for 1,240 additional heavy-duty presses to be distributed throughout the military manufacturing network. The order represented a complete reversal of pre-war manufacturing philosophy. Instead of building equipment to minimum specifications, the government was now demanding machines built to maximum durability standards regardless of cost. By December 1944, Warner and Swasey heavy-duty equipment was operating in 340 factories across 28 states. The machines were producing everything from ammunition components to aircraft parts, stamping operations that demanded reliability under conditions that would destroy conventional equipment. Failure rates averaged 0.3% annually, compared to 47% for lighter competing designs, a performance difference that translated directly into sustained war production capability. Factory managers who had initially complained about the cost and floor space requirements became enthusiastic advocates once they experienced the operational advantages. The Warner and Swasey presses required 85% less maintenance than competing equipment. They maintained dimensional accuracy indefinitely, eliminating the calibration and adjustment cycles that lighter machines required every few weeks. Most importantly, they simply did not fail during critical production runs when replacement parts were unavailable and skilled maintenance personnel were overseas. The commercial implications extended beyond wartime production. Factory managers recognized that equipment capable of surviving continuous wartime operation would last indefinitely in peacetime manufacturing environments. The machines that seemed expensive during initial purchase would prove economical over decades of service life when maintenance costs and downtime were properly calculated. March 12, 1949. The crisis that would validate Robert Hartman's engineering philosophy began not with mechanical failure, but with commercial competition that threatened to destroy everything Warner and Swasey had built. The post-war manufacturing industry was flooding with new equipment, manufacturers promising revolutionary advances through lightweight construction, modern materials, and cost efficiency that made wartime heavy-duty equipment seem obsolete and wastefully over-engineered. American Machine Tool Company had emerged as Warner and Swasey's most aggressive competitor, offering stamping presses at $3,800 per unit compared to Warner and Swasey's $9,200 pricing. AMT's marketing emphasized modern engineering principles, welded steel construction instead of heavy cast iron, aluminum alloy components replacing massive steel parts, and automated controls that reduced operator skill requirements. Industry publications praised AMT's innovative approach as the future of American manufacturing. Hartman watched his order backlog shrink by 6% in 6 months as factory managers chose cheaper modern equipment over Warner & Swasey's heavy-duty machines. The company's board of directors demanded immediate action. "We cannot compete on price against manufacturers building equipment at one-third our production costs," Chairman William Patterson declared at an emergency meeting. "Either we modernize our designs or we close our manufacturing operations." The pressure intensified when AMT secured contracts with 3 major automotive manufacturers who were expanding production capacity for the post-war consumer market. General Motors, Ford, and Chrysler all chose AMT's lightweight presses for their new stamping facilities, citing cost savings that would reduce capital equipment budgets by millions of dollars. The decision seemed to prove that wartime heavy-duty construction was unnecessary for peacetime manufacturing. Hartman argued that the lightweight equipment would fail catastrophically under sustained production loads, but his warnings were dismissed as self-serving complaints from a manufacturer whose products were being rendered obsolete by superior engineering. Industry consultants supported AMT's approach, citing material science advances and structural analysis techniques that made heavy cast-iron construction unnecessary. The consensus was clear. Modern manufacturing required modern equipment, and Warner & Swasey's massive machines represented outdated thinking from a wartime era that no longer applied. The vindication Hartman had been predicting arrived 14 months later with brutal suddenness. On May 23, 1950, an AMT stamping press at Ford's Rouge River plant experienced catastrophic frame failure during a routine production run. The welded steel frame, which AMT's engineers had calculated would provide adequate strength at one-third the weight of cast-iron construction, cracked along a welded seam under loads that were within normal operating parameters. The failure occurred at 2:34 in the afternoon during second-shift operations. The press ram dropped asymmetrically as the frame structure collapsed, destroying $47,000 worth of tooling and injuring 2 operators who were standing near the equipment. Ford's production line was shut down for 11 days while engineers investigated the failure and assessed safety risks from identical AMT presses throughout the facility. The investigation revealed systematic design flaws in AMT's lightweight construction approach. The welded steel frames developed stress concentrations at weld joints where thermal cycling created microscopic cracks that propagated under repeated loading. The aluminum alloy components that reduced weight also reduced vibration damping, causing bearing misalignments that accelerated wear. The automated controls that simplified operation also eliminated the operator feedback that detected developing problems before they became catastrophic failures. Within 3 weeks, AMT presses at GM and Chrysler facilities experienced similar failures. 9 machines suffered frame cracks, 14 experienced bearing seizures, and 23 required emergency clutch replacements after fewer than 500,000 cycles. The automotive manufacturers faced a crisis. The cheap modern equipment they had purchased to reduce costs was creating production disruptions that cost millions of dollars in lost manufacturing capacity. The industry response was swift and comprehensive. AMT's contracts were canceled and the company filed for bankruptcy protection within 8 months. Factory managers who had dismissed Warner & Swasey's heavy-duty equipment as obsolete were now desperate to purchase machines that could survive sustained production loads without catastrophic failures. The order backlog that had shrunk to 47 units in early 1949 reached 340 units by January 1951. More significantly, the AMT failures forced a fundamental reassessment of manufacturing equipment design philosophy. The lightweight, modern machines that had seemed innovative and efficient had proven fragile and unreliable under real production conditions. The heavy-duty wartime equipment that had seemed wastefully over-engineered was actually optimally engineered for the demanding conditions that manufacturing operations actually created. Hartman's vindication was complete, but it came with a sobering recognition of how close the industry had come to abandoning the durability principles that wartime production had validated. November 7, 1952. The research project that would definitively explain why 1940s factory equipment outlasted modern machinery began when Professor Richard Anderson from MIT's Mechanical Engineering Department arrived at Warner & Swasey's Cleveland facility with a proposal that Robert Hartman had been waiting years to hear. Anderson wanted to conduct a comprehensive engineering analysis comparing wartime heavy-duty equipment with post-war lightweight designs to understand exactly why one approach produced machines that lasted generations, while the other created equipment that failed within years. Anderson had followed the AMT equipment failures closely and recognized that they revealed fundamental gaps in modern engineering theory. The structural calculations and material science principles that predicted adequate performance from lightweight designs were somehow missing critical factors that made those predictions unreliable under sustained operational loads. The research would require destructive testing, long-term durability studies, and detailed analysis of equipment that had been operating continuously since 1943. The investigation began with metallurgical analysis of frame materials. Anderson's team discovered that cast iron's graphite flake structure provided vibration, damping properties that were 840% more effective than welded steel construction. When stamping presses cycled, they created vibration forces that propagated through the frame structure. In steel frames, these vibrations reflected off welded joints and created resonance patterns that amplified stress concentrations. In cast iron frames, the graphite flakes absorbed vibration energy and converted it to heat, preventing resonance buildup that would eventually crack lighter materials. The weight that critics had dismissed as excessive served multiple engineering functions beyond simple structural strength. The 47,000-pound cast iron frames had such high thermal mass that temperature variations from continuous operation created negligible dimensional changes. Lighter steel frames expanded and contracted with temperature cycles, creating bearing misalignments that accelerated wear. The mass also provided inertial stability that resisted the shock loads that occurred when presses cycled, reducing dynamic stress on all components. Bearing analysis revealed equally significant differences. Hartman's specification of tapered roller bearings with 340% excess capacity meant that contact stresses remained well below material fatigue limits under all operating conditions. The massive cast iron bearing housings maintained alignment despite frame distortions that would have caused bearing failures in lighter structures. Anderson calculated that the Warner & Swasey bearing systems would achieve 50,000 hours of operation before requiring replacement, compared to 2,800 hours for bearings in lightweight equipment. The gear train investigation produced perhaps the most striking findings. Hartman's decision to oversize gear teeth by 280% reduced contact stresses to levels where material fatigue would require literally billions of loading cycles. Anderson's team calculated that the Warner & Swasey gear trains could theoretically survive 200 years of continuous operation before tooth wear would affect functionality. In contrast, the lighter gears in modern equipment showed measurable wear after 18 months of operation and required replacement after 4 to 6 years. Lubrication system analysis explained why Warner & Swasey equipment survived neglect that destroyed competing machinery. The 40-gallon oil reservoirs provided lubrication capacity for 2,000 operating hours even if operators completely ignored maintenance schedules. The gravity feed design eliminated pump mechanisms that could fail, while the large oil volume maintained stable temperatures that prevented lubricant degradation. Modern equipment with smaller reservoirs and complex pump systems experienced lubrication failures that caused catastrophic bearing damage within hours of pump malfunctions. Anderson's final report, published in the Journal of Mechanical Engineering in June 1953, documented the complete technical explanation for why wartime equipment achieved generational durability. The combination of vibration damping cast iron construction, massive component oversizing, generous lubrication systems, and simple mechanical designs created machines that could absorb operator abuse, maintenance neglect, and continuous high-load operation that would destroy equipment designed to minimum specifications. The research conclusions were unambiguous. The concept of planned obsolescence and minimum specification design was fundamentally flawed for industrial equipment, Machines built with generous safety margins and heavy-duty construction actually cost less over their service life, because reduced maintenance and eliminated failures more than compensated for higher initial manufacturing costs. The industry had spent the 1920s through 1940s optimizing for the wrong objective, minimizing initial cost rather than minimizing total lifetime cost.